I am Avinandan. I will be giving the talk based on our titled Hot Cycle Transversal in Mixed Graphs. This is a joint collaboration with Lawqueen, Kanesh, Jayakrishnan, Madathil, and Saket, Saurabh. So the overview of the talk is as follows. I will first define what mixed graph is. I will mention what our results are, what various problems on mixed graphs have been studied, and then I will talk about the algorithm for hot cycle transversal on mixed graphs. So first I will begin with defining what a mixed graph is. Mixed graph is a generalization of directed and undirected graphs. So it's a three-tuple V, A, and E, where A is the set of arcs and E is the set of edges. So mixed graph contains both arcs and edges. So directed graphs and undirected graphs are special cases of mixed graphs. The problem that we study in this paper is the mixed odd cycle transversal, or in short MOCT, but the input is a n vertex mixed graph G with L arcs and a non-integer and a non-negative integer K. And the question you ask is that whether G has an odd cycle transversal of size at most K. The parameter is K plus L. So we asked whether there exists a set S of size at most K such that G minus S is odd cycle free. This is a generalization of both directed and undirected graphs. Odd cycle transversal has been studied extensively from the point of view of fixed parameter tractability, both in undirected graphs and directed graphs. This model is an attempt to generalize these two graph classes into a single algorithm. So what we show in this paper is that the problem that we have defined here is indeed fixed parameter tractable, parameterized by the solution set size plus the number of arcs, and the runtime is order 2L plus K to the power 2Lk times 2 to the power order K to the power 5. Not very pretty, but that's what we achieved. So now I will try to motivate the problem. The problem motivation is as follows. Algorithm for problems on mixed graphs solve the problems for both directed and undirected graphs. If you look at the algorithms, if you look at the problems, these kind of problems, the cut problems, as we call it, as we will see, or if you have seen a odd cycle transversal in undirected graph, or say a feedback vertex set, these problems generally reduce to some form of cut problem. And the treatment of these problems while dealing with undirected case and directed case are very, very different. Actually, there is no trivial way of reducing one problem to another. This model attempts at generalizing the algorithm to such an extent that there is a one-shot algorithm to solve both the problems on the same problem in both the graph classes. So what kind of problems have been studied before? Well, feedback vertex set has been studied in mixed graph. Well, feedback vertex set has an advantage that both directed and undirected variations are fixed parameter tractable. And Bonsma and Lokstanov in 2011 showed that mixed feedback vertex set is fixed parameter tractable, parameterized by the solution set size. So it's a one-shot algorithm which solves both the directed and the undirected case. We tried to have a similar approach for odd cycle transversal, but then we parameterized by the solution set size, but we do come across a very big problem. The problem is that even though odd cycle transversal in undirected graph is fixed parameter tractable, its directed variant remains W1 hard, parameterized by the solution set size. And therefore, what we initially try to achieve to get a fixed parameter tractable algorithm for mixed graph is not possible, as directed graph is a special case of mixed graph, and an FPT algorithm for mixed graph would immediately imply an FPT algorithm for directed graphs for odd cycle transversal, which would be a contradiction to the fact that directed odd cycle transversal is W1 hard. So we change the parameter, we increase the parameter in some way. We say that, okay, fine, I cannot solve it in terms of the solution set size. So I also add in the number of arcs, which actually in some way create problems. Feedback vertex set in directed graphs and odd cycle transversal in a directed graph reduced to some cut problem. If you have looked, if you know about these algorithms, you will know that DFVS reduces to skewed multi-way cut, and odd cycle transversal, once you do an iterative compression, again turns into some form of cut problem. And we will show that, okay, this is the same thing happens for odd cycle transversal and mixed graphs. It also reduces to some form of a cut problem. We will see what specific cut problem it reduces to. So I will now introduce you bipartition multi-way cut for sets. This is a variant of multi-way cut, a more difficult variant of multi-way cut, where the input is an undirected n vertex graph and a pairwise and a set of pairwise disjoint vertex sets W1 to WP, such that G minus W is bipartite, where W is the union of all these terminal sets, and a non-positive integer K. The question is whether there exists a set of vertices S in V of G minus W such that the cardinality of S is less than or equal to K, such that for every I in P, the reachability graph of Wi after removing S is bipartite, and for every distinct ij in P, there is no path from a vertex in Wi to a vertex in W. Basically, I am trying to disconnect all these Wi's and Wj's while maintaining the property of bipartition in the reachability graph of each Wi. So that is bipartition multi-way cut for sets, which is a multi-way cut for sets with the additional property that the reachability graph is bipartite. And we show that through a series of reductions that our problem of directed multi-way mixed odd cycle transversal actually reduces to this cut problem. And then we solve this cut problem using some specific gadgets. So I will talk about the overview of our algorithm. The first step is, as I said, to reduce to k plus 2l to the power k plus 2l many instances of bipartition multi-way cut for sets. And then step 2, to solve the bipartition multi-way cut for set using some variation of importance separators, as is the case where multi-way cut is solved using importance separators. So now we will see how to design an algorithm. So first, what we do, we separate the graph into two parts. We take the endpoints of the arcs and put it into one set, and the undirected part of the graph we put it into another set. In the undirected, so this is exactly what we did. V of A of G is separated, and then in G minus V of A of G, that is the undirected part of the graph, we ask whether it has and find an odd cycle transversal of size at most k in that undirected graph using the template algorithm that we have. If there is no odd cycle transversal of size at most k, then we immediately say no, because if the undirected part of the graph does not have an odd cycle transversal of bounded size, then the mixed graph definitely will not have an odd cycle transversal of bounded size of size at most k, as the undirected graph is a subgraph of the mixed graph. So we assume that the answer is yes. If the algorithm returns no, we immediately reject the instance and say that there is no odd cycle transversal of size at most k for the mixed graph. In case the answer is yes, we add the odd cycle transversal of the undirected subgraph of the mixed graph into the set of vertices which induce the directed arcs, which induces the arcs. And the set we call as W, which contains the endpoints of the arcs and the odd cycle transversal of the undirected subgraph of the undirected part of the mixed graph. And W size is at most k plus 2L, because if there are L arcs, then there are at most 2L many endpoints, and k is the size of the odd cycle transversal. And now we are in a realm of similar to iterative compression. The schema is very similar to iterative compression, and we will follow the schema of iterative compression. We guess the intersection of the solution with the set W. There are 2 to the power k plus 2L many guesses. And G minus W obviously is odd cycle free, as the set W contains the odd cycle transversal. We delete that guess portion, and now we have a disjoint version of the problem, where I have to find a solution where W star is equal to W minus W double prime, which we guessed and removed. And now we ask the odd cycle the same problem, whether there exists a solution, but it lies completely in G minus W star. Suppose we find a solution Z, the subset of vertices in G minus W, and then how does, okay. So now we have guessed the intersection and removed it from W. Now the question is that, okay, how does a odd cycle free graph look like? And how does G minus Z look like? Suppose we find a solution. It looks like a DAG of strongly connected components. Any directed graph is it can be decomposed into a DAG of strongly connected components, and mixed graph is no different. So it will be a strongly connected component of odd cycle free graphs, which form a DAG. So, and arcs across each direction, whatever. We use the fact that a strongly connected directed graph, which is odd cycle free, is bipartite, and we can generalize this argument of odd cycle freeness in directed graph being bipartite to odd cycle free mixed graphs as well. So a mixed graph which is odd cycle free and strongly connected will be bipartite as well. And the reduction is very simple. You take an arc, you take an edge, and then you replace it with a forward and a backward arc, and the same argument that and then use the template argument that you use for mixed directed graphs. And then you can have a topological ordering, as it is a DAG of strongly connected components. So you can assume that it has a topological ordering. So now we use this structure in our solution. So Z can essentially be partitioned into the subsets of these components. So these components will partition Z into some W1 to W2, W1, W2 up to whatever. So we guess all the partitions of Z, and there are k plus 2L to the power k plus 2L many guesses, because W star size is at most k plus 2L. We guess this partition, and now we find the solution in G minus W star with the following conditions. The first condition is that there is no undirected path from Wi to Wj, because Wi and Wj belong to two different components, strongly connected components. Since it is strongly connected, and strongly connected components, you cannot have a direct undirected path, because then you could have merged these two graphs into one strongly connected component, and the fact that these are two different strongly connected components is violated. And the graph reachable from Wi is bipartite. It's odd cycle free, and essentially we will see that it is actually bipartite. So I hope that you can now see how we are slowly coming towards the bipartition multiway cut for sets. All strongly connected components contain a vertex of W star, whatever, and cut WY to WJ, making sure reachable graph is odd cycle. So now we do a series of reductions. What we do is that we, after guessing these partitions W1 to WP, we remove the directed edges going across W1 to W2 to WP. Because we do not need them, they do not contain any information, and they are just useless because we have to reduce it to a bipartition multiway cut in the undirected graph. So the problem reduces to bipartition multiway cut for sets, which is defined as follows. So we have an input, which is a n vertex graph, and a pair of disjoint vertex sets W1 to WP, such that G minus W is bipartite, where W is the union of the terminal sets. And then we have a non-positive integer, a non-negative integer K, which is the parameter. And we ask the following question: that does there exist a set of vertices S in view of G minus W, whose size is bounded by K, such that the reachability graph of Wi after removing S is bipartite, and for every distinct ij in P, there is these Wi and Wj are disconnected in G minus S. So now we are done with explaining the first step, that is reducing to K plus 2L to the power K plus 2L many instances of bipartition multiway cut for sets. And now we come to the second part of our algorithm, which is how do we solve this bipartition multiway cut? And we'll use a variant of importance separators. So let's first look at multiway cut for sets. So what is the problem? The problem is that you have an undirected graph of n vertices and a pairwise disjoint vertex sets W1 to WP and a positive integer K, which is the parameter. And the question is that does there exist a set S in view of G minus W, where W is the union of the terminal sets of size at most K, such that for every distinct I and J, Wi and Wj are disconnected in G minus S. So here is a pictorial way of representation. So So the idea behind importance separator is that every solution of size at most K contains a W1 W prime separator of size at most K, where W prime is W2 to WP, which is union of I equal to 2 to P, Wi. So what we could do is that we could simply enumerate W1 W1 prime separator of size at most K and then just branch. But the problem is that there can be NCK many separators and choose K many separators, and suddenly we could not the set we cannot simply branch because there are too many sets, and n comes into my runtime and it's not FPT anymore. So this approach doesn't work. This trivial approach doesn't work. So the big idea which Daniel Marks came up with in 2006 was to say that, oh, we do not need to go over all separators, but we need to go over, there exists a solution which contains there exists a solution for the bipartition multiway cut for sets, which contains an importance separator. So we can just count the importance separators. And as we will see, the important number of such importance separators is bounded by 4 to the power K. Importance separators of size at most K are bounded by 4 to the power K. So how do we define importance separators? Importance separators are defined as follows. Sorry. S1 and S2 are W1 prime separators. So first we define the notion of domination. S2 dominates S1 if S2 is minimal, inclusion-wise minimal, and the cardinality of S2 is less than equal to cardinality of S1, and reachability graph of W1 after removing S2 is a superset of reachability graph of W1 after removing S1. And S2 is an importance separator if no W1 W prime separator dominates S2. So basically, you are trying to push this separator W1 prime separator as far as possible from W1. And at the point where you cannot push any further, that separator is called the important separator. Small separator farthest from W1. That's how we define it. But if we had to count every W1 W prime separator, then it would have, again, as we have said, it would have been bounded by NCK, which is n to the power k. But number of important separators, W1 W prime separators of size at most k, is bounded by 4 to the power k. I am not going into the details of how this came in. If you are interested, you can look at Marx 2006. This paper, I think, was published in Soda. In the same paper, he suggests that he proves that there is an optimal solution for multiway cut for sets that contain an important W1 W1 prime separator. So again, the input is G W1 to WP and the parameter K, and W prime is the union of I from 2 to P WI, and you branch on all these 4 to the power K separators and then recurse. Once you find it, for each sub-instance, you just recurse. The measure is K and it drops every time. So now we look at, since we have a small detour for multiway cut for sets, now we look at bipartition multiway cut for sets. Same problem as multiway cut with the additional property that the reachability graph of the terminal sets for each terminal set is bipartite. So we use a generalization of importance separators, which we call as augmented importance separator. And this idea was first coined in the paper of Lawqueen and Ramanujam in 2012, ICAL. So let us recall the definition of domination. So we will modify these definitions. So there are two separators, S1 and S2, which separate W1 and W1 prime. And S2 dominates S1 if S2 is minimal, cardinality of S2 is less than equal to cardinality of S1, and the reachability graph of W1 after removing S2 is a strict superset of reachability graph of W prime after removing S1. But here we add additional constraint, one additional constraint, which is odd cycle transversal of the reachability graph of W1 after removing S2 is less than the reachability graph of odd cycle transversal of the reachability graph of W1 after removing S1. And we call these kind of separators well domination maximal separator. Just an additional condition because we have to maintain the bipartition property. So this is needed. So the idea is that small separator farthest from W1, but with a small odd cycle transversal in the reachability graph. Well, it becomes a bit more tricky. What Lawqueen and Ramanujam show is that there is a set of a covering set, or should I say, I don't know if I should call it a covering set, but there is a set of size 2 to the power order k cube, which intersects all domination maximal W1 W prime separators of size at most k. And that immediately means that you can just branch on this set and reduce your measure, which is k, which is 2k minus lambda. So what is Lawqueen-Ramanujam algorithm? It is an input which has the graph G, the terminal set W1 and terminal set W prime, and the parameter K. And the algorithm runs in 2 to the power order K cube and to the power order 1, and either returns a set which is disjoint from W1 union W1 and W prime, such that either the set is bounded by 2 to the power order K cube, and it intersects all domination maximal W1 W prime separators of size at most k, or it says that there is no well domination maximal separator of size at most k. What we show is that There is an optimal solution for bipartition multiway cut for sets which contains a well domination W1 W prime separator, and that immediately solves our problem. We just use the Lawqueen of Ramanujan algorithm as a black box, and then we just do a branching, which is a template thing. So the idea behind our algorithm is that there is an optimal solution which intersects the set, and then we branch the set of subsets of the set of size at most k. So what our algorithm is as follows. We have an input where we have a graph and the terminal sets W1 to W3 and a positive integer k, which is a parameter. Let W prime be the union of Wi from I equal to 2 to p. If all the Wi's are disconnected from each other, and the reachability graph of each Wi is bipartite, then we do not have to do anything. We just say yes and terminate. If W1 is disconnected from all other Wi's and reachability graph of W1 is bipartite, then you just remove the reachability graph of W1 and recurse on the rest of the terminals and the rest of the graph and rest of the terminals. Else, sorry, apply the Lawqueen of Ramanujan algorithm on G, W1, W prime, and parameter K. If it returns a set, then branch on all subsets of the set of size at most K and recurse. Otherwise, and after finishing the recursion, if everything is not, if you are not accepting in any of these recursions, then just return no at the end of the branch. The runtime of the algorithm, which I will not talk about, if you recurse over it, you will see it forms an equation, and if you solve it, it can be solved in 2 to the power order k to the power 5. Ignoring the polynomial terms as we do in parameterized algorithms. So we again show that given an instance of bipartition multiway cut for sets, how do we give an overview of an algorithm which runs in 2 to the power order k to the power 5. And there are at most to k plus 2l to the power k plus 2l many instances of the bipartition multiway cut for sets. So we just use our algorithm for each of the set, and then if any of these sets return yes, we say yes. If none of these instances return yes, then we simply say no. There is no odd cycle transversal mix for the mixed graph of size at most k. That's an overview of an algorithm and the end of our talk. This was the contribution of our project. Thank you.